Welcome to The Explainer. Today, we're pointing our lens at literally one of the most stunning, mind-bending objects predicted by the mathematics of physics. I mean, we're all pretty familiar with black holes, right? Those infinitely powerful cosmic vacuums that just swallow everything. But what if I told you that the exact same equations governing black holes also mathematically prove the existence of their absolute opposite? We're talking about an object that acts like a massive cosmic geyser, violently expelling matter and energy out into the universe, all while remaining completely impenetrable from the outside. It totally sounds like science fiction, I know, but this is a very real question posed right inside Einstein's general theory of relativity. Honestly, what exactly happens if you run a black hole backward in time? The answer isn't just some quirky mathematical loophole. It's a profound journey. And as you'll see, it might actually explain the absolute biggest unsolved mysteries of our cosmos, from dark matter all the way to the very origin of the universe itself. Okay, let's dive into this roadmap. First up, we'll define the ultimate cosmic fountain. Then we'll look at the math behind the madness, tackle the classical instability problem, explore the quantum gravity bounce, and finally tie it all together with dark matter and big bangs. So, part 1, the ultimate cosmic fountain. To really wrap our heads around this abstract idea, we need to ground it in something we already intuitively understand. Check out the perfect symmetry here. A black hole has what we call a future singularity. Basically, it lies in the future of all infalling matter. Once you cross that event horizon, you inevitably hit the singularity. End of story. But a white hole? It has a past singularity. Matter doesn't fall toward it, matter violently flies away from it. So while a black hole has a future event horizon that nothing can ever exit, a white hole has a past event horizon that absolutely nothing can ever enter. But here's the absolute kicker. From the outside, they have the exact same mass, charge, and spin. If you were floating out in space, safely looking at a white hole from a distance, its gravitational pull would bend light and attract you exactly like a black hole of the very same mass. The entire difference is just in the one-way street of its horizon. Moving right along to part 2, the math behind the madness. Now you might be wondering, who actually came up with this? It definitely wasn't some sci-fi novelist looking for a cool plot device. Einstein published his general theory of relativity back in 1915, and literally mere weeks later, in 1916, Carl Schwarzschild found the first exact solution to those equations, predicting what we now know as a black hole. But here's the thing. Einstein's field equations are perfectly time-symmetric. If you take a valid solution and mathematically reverse the direction of time, you get another perfectly valid solution. Fast forward to 1960, and we hit a massive milestone, which actually sets the stage for some brand new, cutting-edge discoveries in unimodular gravity happening right now in 2025. And this brilliantly illustrates a true mathematical masterpiece. Martin Kruskal and George Shekaris independently developed a new coordinate system that basically stretched Schwarzschild's math to its absolute limits. By removing these artificial mathematical defects, they revealed a maximally extended spacetime containing 4 distinct regions. You've got our exterior universe, the black hole interior, a parallel causally disconnected universe, and then a 4th region, the white hole interior pointing toward the past. This math even revealed the famous Einstein-Rosen bridge, a wormhole connecting our universe to that parallel one right through these interiors. Which brings us to part 3, the classical instability problem. So here is the central conflict of all this. If white holes are mathematically perfect, why haven't we ever actually observed one? Well, the first major hurdle is the second law of thermodynamics. You know, the rule that dictates that in an isolated system, disorder or entropy must always increase. Think of a black hole kind of like a teenager's messy room. It absorbs disordered matter, which increases its entropy. A white hole doing the exact reverse would be like watching that messy room just spontaneously clean itself. It would have to take disordered matter and eject it in a more ordered state, without any apparent energy input. Now, while this isn't fundamentally forbidden by physics, it requires astronomically improbable low entropy initial conditions. The universe would basically have to be fine-tuned to an absurd degree just to create one. But the real fatal blow to classical white holes? That came from physicist Douglas Eardley back in 1974. He mathematically proved that even if a white hole somehow did form, it would be profoundly unstable. Just picture a white hole sitting out there in space. Our universe is completely filled with radiation, right? Like the cosmic microwave background? Well, because nothing can actually enter the white hole's horizon, any radiation falling toward it just violently accumulates right on the boundary. Through a process called gravitational blue shifting, even a single solitary photon of light would be concentrated to infinite energy density right at the horizon. And the result? the white hole would instantly collapse right back into a black hole. So classically speaking, they destroy themselves the very second they interact with our universe. All right, moving into part 4, the quantum gravity bounce. So is that just it? End of the story? Well, not quite. Because classical physics completely breaks down at the center of a black hole anyway. We have to pivot to our ultimate quantum salvation, loop quantum gravity, or LQG for short. This is one of the leading candidate theories trying to finally unify general relativity with quantum mechanics. LQG proposes that spacetime itself isn't just this smooth, continuous fabric. Instead, it's quantized into discrete loops at the unimaginably tiny Planck scale. Think of them as the fundamental atoms of space. And because space has a minimum possible size, gravity literally cannot compress matter into an infinitely dense point. The infinite singularity, it's completely prevented. Let's move to see how this builds a completely new, mind-bending life cycle for a black hole. Step 1, matter collapses, forming your standard black hole. Step 2, that matter continues compressing inward until it hits the absolute limit allowed by quantum mechanics. Step 3, at this precise moment, quantum geometric effects create a massive, overwhelming repulsive force, triggering what's called a bounce. It forms this momentary state known as a Planck star. And finally, step 4. The matter bounces back outward, erupting as a white hole. You heard that right. The black hole literally transitions into a white hole. And the density at which this bounce happens is just staggeringly huge. 10 to the 93rd power kilograms per cubic meter. That is the Planck density. To put that into perspective, at this unimaginable compression, the matter inside the hole acts exactly like a giant, tightly coiled spring, absolutely packed with potential energy, just waiting to explosively bounce outward. But wait a second, you're probably asking, if black holes are constantly bouncing into white holes, why do we still see black holes everywhere? Well, the answer is extreme gravitational time dilation. For the matter actually inside the black hole, this entire collapse and bounce process takes only microseconds. But because extreme gravity severely warps time, an outside observer, like us, looking at a stellar mass black hole, would have to wait billions or even trillions of years just to see that microsecond bounce actually happen. The universe simply isn't old enough yet for us to see the white hole eruptions of typical stellar black holes. Let's wrap things up with part 5, dark matter and big bangs. Now, what's really interesting about this is that this realization leads us directly to a place where these invisible quantum remnants might actually solve the universe's absolute greatest mysteries. Just look at this massive chunk of the universe's energy pie chart that is simply missing. Roughly 27% of our universe's total energy content is made of dark matter. We know it has a huge gravitational influence. I mean, it literally holds galaxies together, but it completely ignores light, and we have never managed to detect a single particle of it. Well, a brilliant proposal by physicists Carlo Rovelli and Francesca Vidato suggests that dark matter might actually just be tiny white holes. Think about it. In the completely chaotic first fractions of a second of the early universe, tiny primordial black holes could have easily formed. And because they were so small, their bounce clock was way, way shorter. They would have already evaporated down to the Planck mass and tunneled into white hole remnants by now. Today, these ancient relics would have a tiny Planck-scale exterior, but a massive interior volume holding all the information they ever swallowed. They'd be massive enough to provide the extra gravity we see, but so incredibly small, they'd be entirely invisible to our telescopes. A perfect fit. And the science on this is evolving incredibly fast. In fact, just in 2025, a landmark paper published in Physical Review Letters examined this exact transition using a framework called unimodular gravity. Basically, this is a modification of Einstein's equations that fixes the determinant of the metric tensor, which seamlessly solves some major cosmological problems. The researchers mathematically proved that under this framework, black hole singularities naturally resolve into white holes that actively eject matter and time. And even more astonishingly, this research actually connects these white hole transitions directly to the nature of dark energy, the mysterious force that's actively accelerating the expansion of our entire universe. Talk about a game changer. It completely reframes how we view reality. As the philosopher of physics Hugh Price so beautifully put it, the arrow of time is a cosmological accident. Think about that for a second. The whole reason we experience time moving strictly forward, and the reason we clearly see black holes but absolutely none of their white hole twins, isn't because the fundamental laws of physics forbid it. No, it's simply because our universe started out in a highly specific, very low entropy state. Which leaves us with one final, totally awe-inspiring thought. If a white hole is mathematically defined as a past singularity from which matter and energy explosively emerge, and into which absolutely nothing can ever return, doesn't that sound exactly like the origin of our universe? In loop quantum cosmology, the Big Bang is actually replaced by a big bounce. So the ultimate takeaway here is that perhaps we haven't failed to observe a white hole at all. Perhaps we are literally living inside the debris of the ultimate time-reversed cosmic fountain right now. Was the Big Bang just the ultimate white hole? I'll leave you to ponder that. Thanks so much for exploring this with me today.